All right, our final presentation for today is from Ricardo Jesus. Ricardo is a PhD student with Michelle Weiland at the University of Edinburgh Parallel Computing Centre, working on performance analysis and benchmarking for Chapel.
Hello, everyone. My name is Ricardo Jesus. I'm a PhD student from UPCC. And today I'm going to talk about ChapelPerf, a performance suite for Chapel. And this is roughly the outline that I will follow. So just to briefly introduce and motivate our work, we all know how hard application porting and performance optimization can be, especially so in the field of HPC. And this is mainly due to the huge variety of HPC codes that exist, all the different requirements that they have, all the different systems and system architectures where those codes are meant to run, as well as all other nuances at all scales which affect performance. So one way we HPC programmers have found to cope with these complexities via high-level parallel programming languages, libraries, and runtimes, of which Chapel is a very good example, of course. But these high-level parallel programming frameworks, they bring new challenges to the table as well. Namely, how do we know if a given parallel programming framework is good for a specific class of problems? Or how do we know if it delivers good performance across different system architectures? And how do we compare a given programming framework to another? Of course, here we are interested in answering these questions from the viewpoint of Chapel. And in my opinion, a very good way of doing so is via benchmarking. And this brings us to RAJAPerf.
Sorry, a quick note. I think there's a window on the right-hand side in front of your presentation. It's blocking a little bit of the slides.
I can't see anything, sorry. Is it this window?
Yeah, that's the one. Yeah, maybe move it to somewhere.
I'm gonna move it.
Yeah, okay.
All right, thanks. So, and as I was saying, so this brings us to RAJAPerf, which is the Raja performance suite. So as its name suggests, RAJAPerf was originally developed to assess the performance of Raja, which is a performance portability layer for C++. And RAJAPerf contains over 50 loop-based kernels extracted from HPC applications and other benchmark suites. And importantly, each kernel in RAJAPerf is implemented in a number of what they call variants, which essentially correspond to different programming models and frameworks. So typically, each of these 50 kernels is implemented in baseline sequential implementations, baseline OpenMP implementations, CHIUW, heap, and then variations that utilize lambda functions to implement the loop bodies of the main variants. And then, of course, variants that utilize Raja to implement the kernels. And so it's this wide coverage of both in terms of code patterns that it considers and programming models that it implements that, in my opinion, make it a very good tool in which to look into these questions, which in turn takes us to ChapelPerf, which can be understood as the Chapel incarnation of RAJAPerf. So as of now, ChapelPerf is a mostly complete port of RAJAPerf to Chapel, and we developed it mainly to essentially to extend the wide coverage offered by RAJAPerf, both in terms of code patterns and programming models that it contemplates, to the Chapel ecosystem. So far, we have fully implemented 2 main variants of each kernel in Chapel, which correspond to baseline Chapel sequential implementations, and for all Chapel, which is the baseline parallel implementation in Chapel, which is analogous to the base OpenMP variant of RAJAPerf. We've developed ChapelPerf to be a drop-in replacement for RAJAPerf, and so it accepts the same command line options that RAJAPerf also does, generates the same outputs in the same formats as RAJAPerf so that you can easily compare both. So now I have a few slides about describing the experience of porting RAJAPerf to Chapel. And I can say that overall it was a very straightforward process. Porting most kernels was just a matter of adapting the C++ code to Chapel syntax. And the same can be said about the logic around the kernels themselves, by which I mean the way the RAJAPerf code is organized in terms of class hierarchies, the way the execution of the kernels is driven, the way the kernels interact, and so on. And this is because, RAJAPerf utilizes things such as inheritance, polymorphism, and C++ containers, for example, to implement these things. But Chapel offers closed analogs. So it's just a matter of often translating those implementations in C++ to Chapel's equivalent features and making everything work together. So here I have an example with the AppSphere kernel. This is the reference C++ implementation from RAJAPerf, and obtaining an equivalent, essentially Chapel implementation is just a matter of changing the syntax of the for loops. Now to obtain the parallel version, the baseline OpenMP version would be obtained by having this program over here, We can do that in CHAPEL by replacing this for with the for all, for example, or in this case, we can also replace the body of the loop here by this line over here, where we utilize a reduction operator there to perform the dot product here, which is a lot more concise and explicit. But of course, there were a few challenges along the way. So one of them had to do with aliasing array views. So in C and C++, it's very easy to declare pointers that essentially alias a given region of memory. So for example, here, this is extracted from the mass3dpa kernel. Here they are declaring 3 pointers to the arrays of different inner dimensions that alias the same SM1 array. And this is quite easy to do in C++, as I'm showing here. Doing the same in CHAPEL in a straightforward manner it's not really possible right now. So one of the workarounds that we found was via inline procedures, where essentially we declare the procedure which captures the underlying array that we want to alias. Then we perform the index arithmetic explicitly inside the procedure. Another option that we also consider is via a class that wraps the underlying array, and then perform the index arithmetic inside the class is this method. None of these options are particularly good. So they work for simple cases, but they're not particularly good. That's because they are not a full-blown array class. And so we lose things such as promotion-based operations. We lose things such as easily iterating over these arrays and things like that. So I think it would be good if CHAPEL could support this type of aliasing, at least in simple cases such as the ones here, where we are going from a 1D array to a multi-dimensional reference type alias. Another issue that we found was with the lack of the long double type in CHAPEL. So RAJAPerf uses these types extensively to compute checksums of the runs, and then to verify and ensure that all varieties, that all variants of the kernels execute correctly and are implemented correctly. So what we did was we took the partial implementation of long doubles that CHAPEL has for its LCALS benchmark, and we extended it essentially to increase the interoperability of our long double type with other native CHAPEL types, and to be able to perform I/O with long doubles directly. Again, I think it would be useful and it would make sense if CHAPEL included the long double type as a C type, like how it currently does with a C string or a C size T, for example. And now I have some very preliminary performance results. Which I took using the ChapelPerf to assess the performance of CHAPEL. These are the systems that I've considered. They are an HP Cray EX system, HP Apollo 7, HP Apollo 80. This is a compiler that I use to compile both CHAPEL, both as the backend compiler for CHAPEL, and to compile RAJAPerf itself. And these are the corresponding optimization flags that I used in all cases. And so here I'm plotting the running time of the base CHAPEL variant normalized to the time of the reference C++ implementation of the kernels. And at the bottom, I have something similar, but with the running time of the for all CHAPEL variant normalized to the running time of the base OpenMP variant. And so mind the log scale. So ideally here, all kernels, all data points would lie on the black lines here, meaning that both the sequential variants and both OpenMP parallel for all and OpenMP variants achieve roughly the same performance. And we can see that in a lot of kernels, this is indeed what happens, but there are a few exceptions of kernels where CHAPEL performs significantly worse sometimes than the reference C++ and OpenMP variants. This is particularly common here in the apps kernels, which often correspond to kernels that are more complex than the other kernels, and which might even utilize data structures such as lists or sets or something like that. And this drop in performance in CHAPEL is also more common when comparing the for all CHAPEL variant with the baseline OpenMP variant. You can see that CHAPEL often trails behind the OpenMP variant by a factor of 2, 3, sometimes 10, 100, and 1,000. And now some quick conclusions. So as I've just said, I've presented ChapelPerf, which is an implementation of the RAJAPerf kernels in CHAPEL. It's meant to be a drop-in replacement for RAJAPerf. And we've developed it with the idea of extending the wide coverage offered by RAJAPerf in terms of kernels, of code patterns, and programming models to the CHAPEL ecosystem. Also shown some preliminary results using this benchmark that show that CHAPEL in general performs well compared to the reference C++ and OpenMP implementations, though there are a few kernels in which CHAPEL sometimes suffers big slowdowns compared to the reference implementations. So of course, this is very early work, it's ongoing work, and some of the next steps that you want to take are to study these cases in which CHAPEL shows significant slowdowns and address them, and also to implement more variants of the kernels, namely idiomatic variants in which we explore the promotion and reduction-based data parallelism features that CHAPEL offers, as well as implement some GPU-based and multi-node-based variants of the kernels. And this concludes my presentation. Thank you very much for your attention. Now, if anyone has any questions, I'd be glad to answer them.
Yeah, if you have questions, please unmute or raise your hand. Thanks, Ricardo.
Thank you.
Okay, well, I have a question if no one's got their hand up right now. Could you say a little bit more about performance portability? So you mentioned that CHAPEL does comparatively worse on ARM-based systems. Do you know, have you identified there's particular features of CHAPEL that are not performance portable to the ARM systems?
No, not yet. That's part of the ongoing work. So for example, I draw that conclusion based on the green data points here. So both Fulham, which is an HP Opal 70, and Eisenbach 2, which is an HP Opal 80 systems, are ARM-based. This one has standard X2 processors, and this one has A64FX processors. And you can see that usually the kernels in which CHAPEL does worse, it does worse in the ARM-based systems. I don't know if, for example, these data points here are lack of vectorization. This is something that we want to explore in future work. But this is the main conclusions that we can take from observing these and similar plots. So here, of course, I couldn't put everything, right? So this is just comparing the baseline CHAPEL implementations with reference sequential C++ implementations and OpenMP there. But you can see that often the systems that do worse are the ARM-based ones. And often when CHAPEL does better, that's also the case, it usually does better on the x86 one, as you can see there, for example. So I do agree that in principle, there should be nothing preventing CHAPEL from performing as well in ARM as it does in any other system. But apparently, according to these preliminary results, there are a few kernels in which it's doing considerably worse. So again, mind the log scale. So this means that it's doing 10 times, that CHAPEL in these cases, for example, is being 10 times slower than the reference C++ implementation. And the x86-based system, for example, doesn't show these slowdowns. So that's where I'm coming from.
There's a lot of data points there to investigate.
Yeah.
Engin has a question?
No, yeah, true.
Yeah, I'm sorry if you gave the answer in your talk, but I think I saw that you were using C backend with 126. Was there any particular reason that you are sticking with C backend?
No, no particular reason. I mean, these are just, I mean, in particular for this slide, I use the C backend to keep consistency, to say that I use the same compiler, the same versions, and essentially the same flags, because I also made sure that the CHAPEL is relaying the same optimization flags to the C backend. So I just wanted to make sure that in these runs, everything was compiled with the same compiler. But I've also run tests with the LLVM backend, and I obtained similar results. So that's not the main factor here. It's not the backend compiler.
Thanks.
Yeah, no worries. Thanks.
Brad.
Yeah, so a few of us here were trying to absorb the request you made about the array views, and somebody on the team was asserting like, well, we have ways to alias arrays, but is it correct that the challenge you ran into, if I'm remembering correctly, was that you wanted to start with a 1D array or its memory and basically view its elements as though they were a multidimensional array? Is that the case that we're missing?
Yes. So it's not just pure aliasing as in a reindexing. I do know that CHAPEL supports reindexing, but that's from say a 1D array to a 1D array. Here I'm talking this sort of multi-dimensional aliasing, where you go from a 1D array, which is a block of memory, right? Then you can declare pointers to 2D arrays of whatever dimensions, inner dimensions you want, and you just alias the same block of memory. So that's where I'm coming from. Yeah.
Okay.
Maybe I should have been more explicit, but that's the main point here.
That's fine. Yeah, I mean, and thanks for clarifying. Yeah, and I mean, I don't think this helps you, but we do have the ability to go from a higher dimensional array. Well, no, do we? You can take a higher dimensional array and you can take a slice of it as though it were a lower dimensional array. But I don't think there's a way to kind of say, let me take the buffer of this higher dimensional array and view it as a 1D, view the whole thing as a 1D array. So kind of like a memory-based reshaping, I agree, is something we don't have today. And you're not the first user to ask for it. The follow-up question I had there was, is that aliasing property something that is very, what do I want to say, like intrinsic to the kind of computation the benchmark's doing? Or like when we ported LCALs, they had similar kind of patterns, and it felt almost like it was just sort of like, I don't know, like almost C laziness of like just wanting to kind of manage memory manually, as opposed to like anything sort of that related to kind of, you know, the end user's computational pattern or whatever. Do you know which case it is here necessarily?
So I don't think it's C laziness. So I do think this sort of reshaping, it's very common, and even Python has it, for example.
Okay.
So can you do without it? Well, in general, yes, I suppose you can always find workarounds, right? But I do think that having this sort of simple remappings, it's kind of nice. It's kind of nice to have, because it's kind of easy to think of a memory block of an array of data, and you just want to interpret it. If you have, I don't know, 1,000 elements, maybe you just want to interpret it as a 10 by 10 by 10 cube or something like that. And in conceptually speaking, of course, I'm not talking about code, but conceptually speaking, it's a rather simple operation, right? So if you have 1,000 elements and you want to have 10 by 10 by 10, I mean, it's the same thing. So that's where I'm coming from. And also, I also noted that this sort of, for example, using workarounds such as inline procedures or even proper classes to wrap the arrays, they tend to generate significantly worse performance. So I do think that these solutions are also not good, because they don't let the compiler infer enough information to generate efficient code. So yeah, so that's also important from that viewpoint.
Okay, great. And to be clear, in asking, I wasn't trying to seem a counter to the idea of having such a feature. And as I said, others have definitely brought it up as well as the ability to like create an array that adopts memory from somewhere else or can sort of give up its memory to something else. So I think that there is sort of a theme there that we're lacking that we'll need to add. Really, it was more just kind of about the usage in this benchmark, whether they felt like, you know, like sound uses or just kind of like manual memory management uses. Sounds like more like the former from what you're saying. So thanks very much.
All right, no worries, thanks.
Thanks again, Ricardo.